Okay, so now we're going to continue our look at calculating electric potential by looking at how to find the electric potential around a charged sphere and around a system of multiple source charges. So let's just jump right on into it. Okay, so we're looking at a charged sphere, something like a Van de Graaff generator. The electric field outside a charged sphere is the same as that of a point charge. So consequently, the electric potential outside a charged sphere is given by the same equation as the one for a point charge. That is, when we're dealing with a charged sphere, we can treat it kind of like it's a big point charge. And we can use K, Q over R, where Q is our big charged sphere. We can kind of cast this result in a more useful form. It's common to charge a metal object, such as a sphere, to a certain potential. For instance, this can be done by connecting a sphere to, say, a 30-volt battery. This potential, then, the 30 volts, which we're going to call V naught, is the potential right on the surface of the sphere. So we can see then from this equation that is equal to this right here. Okay, in this, the large r is the radius of the sphere, and the small r is in the initial equation is the distance away from a point charge. We're saying here that the distance away is the same as the radius of the charged sphere. So a sphere of radius big R that is charged to a potential V naught has the total charge 4 pi epsilon naught R V naught. And if we substitute this expression for Q into this equation here, we get the electric potential of a sphere. So this equation tells us that the electric potential of a charged sphere is equal to the electric potential that we charge it to on the surface and decreases inversely with the distance away from the sphere. So the electric potential at a distance 3 times the radius of the sphere is 1/3 that of the electric potential at its surface. Now, a quick look at the learning objectives at the front of this video and in your reading packet for a charged sphere. You would see that it tells us that really we're looking to be able to describe and sketch a graph of the electric field and potential inside and outside a charged conducting sphere. So you're not going to have to worry too much about calculating the electric potential of a charged sphere. It's more describing and sketching a graph of the electric field and potential inside and outside a charged conducting sphere. And here is just such a graph. We can see then that the electric potential increases as you get closer to the sphere, remains constant through the sphere, and decreases as you move away from the sphere. And that's all this is telling us over here. And since we're asked to describe and sketch a graph of the electric field and the electric potential, we have to compare the two, which we can see here, where the electric field of a sphere increases as you get to the sphere, drops to 0 in the sphere, and then it decreases as you move away from the sphere. And then again, here's the electric potential. So make sure you take a look at those. And we're going to go ahead and move on to looking at calculating the electric potential of several point charges. Now that we have some understanding of calculating the electric potential around a single point charge, we can look at how to calculate the electric potential around multiple charges. Basically, the electric potential at a point in space is the sum of the potentials due to each charge. In other words, we use the superposition principle. Now, as you just heard me say the words superposition principle, and you see them there on the screen, I can practically hear a collective groan of dismay as you recall all the fun we had with it while learning about Coulomb's law and electric fields. Rest easy though, because in regards to electric potential, things are a bit easier than with Coulomb's law and electric fields. You see, those two fellows deal with vectors and required us to superimpose force vectors and electric field vectors, which meant we had to split forces and fields into components and do all that wonderful stuff. Electric potential, though, is a scalar. So we can use the superposition principle by simply taking the algebraic sum of the electric potentials of each of the charges, which is good news for you, physics learner. So, since the total electric potential at some point near several point charges is just the algebraic sum of the electric potentials from each of the charges, we use an equation in this form here, where we've got the electric potential is equal to, this is really just our K constant. It's the individual sums of the charge over the distance away from that specific point that we're looking for. This is the form of this equation that you have on your equation sheet. So let's take a look at an example of how to use it. Okay, so in this example we have this point away from two charges. The two charges are a 2 nanocoulomb charge that's 5 centimeters away from a point, and a negative 1 nanocoulomb charge 4 centimeters away from a point. And we're asked to figure out the electric potential at this point. So what we have to be able to accomplish this is our equation for finding the electric potential in the vicinity around a series of point charges. Now all this equation means here is this is the individual sum of the electric potential of each point that is around that point that we're looking at. Okay? And as we look at this, if we take a look at our equation sheet, this 1 over 4 pi epsilon naught is really just Coulomb's constant K. So when we go to apply this equation to this situation, we're going to end up looking at something like this here, where we've got our electric potential and we've got the KQ over R for each of those charges at that point. And we can factor out the Coulomb's constant and we end up with this right here. So we can see right from the start that this is a whole lot more simpler than dealing with Coulomb's law or finding the electric field at a point, because this is a scalar. It's just the algebraic sum of the electric potentials at all of these points. We don't have to worry about splitting components or making or doing vector resolution or anything like that. We're just going to add up the electric potentials from these charges at that point. So substituting in our Coulomb's law constant here, we make sure that we have times 10 to the negative 9 on each of those charges, because they're nanocoulombs. Nano means times 10 to the negative 9, and we've converted our centimeters to meters. We end up with a potential difference then, or an electric potential of 135 volts at that point away from those two charges. So as we can see from this example, it's really quite simple to find the electric potential at some point around charges. We'll see this and other examples like this in class. We'll see you then.